Okay, let's look at how to find the largest eigenvalue of a given for a given matrix A, and we'll find this using the power iteration method. So we start with the sample matrix A, and generally if you want to find the eigenvalues and eigenvector, you would use the NumPy package. So np.linearalgebra.eig. You can use this function to find the eigenvalue and eigenvector. So the first array is the eigenvalues, and the matrix that is shown below is the corresponding eigenvector. So let's store this in E for eigenvalue and V for eigenvector. The one we are interested in is the largest eigenvalue, so that's the first one in this case, so that's E of 0. And the corresponding eigenvector is this one, the first column, so that's V of all comma 0. So let's get started. We need to use the power iteration method to come up with the same eigenvalue and the eigenvector. The way the power iteration method works is very simple. All you do is you transform the vector x using the matrix A. You can do that by using the dot product between A and x, and then you store this value into x. Then you do this repeatedly and you look for the highest value within the vector. So you can look at the max of x, and to make sure we are interested in the magnitude, not the direction or not the sign, so we will take the absolute of our x vector to make sure we capture the large magnitude values. Now the issue with this is so this is our eigenvalue, okay, and if you apply this repeatedly you should converge on the eigenvalue. The issue with this is as time goes by, this value gets very large and unrealistic. To prevent this from happening, what you need to do is you need to normalize your x vector. You can do that by dividing it by the eigenvalue itself to get the normalized version. And I mean reinitialize A and x. And then you can see it starts at some number, and then as I repeatedly compute it, it gets closer and closer to the highest eigenvalue. Now you can also print the eigenvector. So print eigenvalue comma eigenvector is x in this particular case. So reinitialize this, and you can see how it's quite similar to the one over here. Now to get this one, the actual eigenvector, you shouldn't be using this function. You should look at the length of the eigenvector. So we can use that for normalizing our eigenvector. So this should have been np.linearalgebra.norm of x. Okay, so reinitialize this. Okay, and as you repeatedly do this process, you can see how it converges closer and closer to the eigenvector that we calculated previously. Okay, so this is basically the essence of finding eigenvalue using the power iteration method. So you can put this inside a loop now. So for I in range of max iterations. Okay, and all these go inside it. And we need to define this. So let's say we want to do this 10 times. And you can see it's going to converge to the maximum eigenvalue. To put all this information inside a table, we don't care about the eigenvector for now. We care about the error, the relative error. So we need to define our relative error function. Define error. So the error is going to be relative error between the eigenvalue and old eigenvalue. Okay, old eigenvalue will be reset at the end of the code inside the for loop, and you need to initialize it here with some number. So let's just put in 0. Oh no, don't put in 0. Yeah, let's put in 0. And instead of x, let's print the error now. Oh, sorry, old eigenvalue. Okay, so you can see the relative error becomes smaller and smaller the more you compute it. To put it inside a pandas data frame, first import pandas as PD, and we'll create a result data frame, PD dot data frame columns equal to eigenvalue and error. Okay, eigenvalue with small p. Okay, and then you can just insert that in. Instead of printing it over here, we'll just say result dot location and I for the iteration number equal to eigenvalue and the error. Okay, and at the end we can show the results table, and here you have the results. Now it might be good to stop the iteration once you reach a minimum error tolerance. So let's say we have some kind of error tolerance equal to, let's say, 5% or 0.5%, and so once you hit the error tolerance, you would like to stop it. So if error is less than error tolerance, then just break. Okay, there you have it. So once you fall below the a set error tolerance, it will exit, and that will be your final answer. Okay.